Welcome back. Hope you're excited. This is CSCE 611. My name is Jason Bakos. I'm the instructor. One of my two TAs is down there, Soyash Singh. The other one is Angela Kalinko, who you'll meet on Wednesday or Friday, depending on what your lab you're in. So we'll quickly just go over the syllabus. Most of this is just boilerplate. I think we got the catalog description there. If you're in section 1, then you'll meet here on Monday and you'll meet in the lab on Wednesday. The lab is Swearingen 3D22. And if you're in section 2, you'll meet here on Monday and you'll meet in the lab on Friday. The lab door combination is actually incorrect. I just realized that they've changed it. So the new lab door combination for 3D22 is 45213. It's usually propped open during regular business hours. So ignore the combination on the syllabus. I'm sorry about that. I use the departmental Moodle site for everything. I don't use Blackboard. So everything you'll need is on Moodle. It's dropbox.csc.sc.edu. If you have any problems logging in there, which may be the case if you're from outside computer science and engineering, then contact Ryan Austin for help. And I have his email address there. Hold on, guys. Hold up the syllabus.
Sorry, I went to the wrong front.
Oh, no problem. I just got started. Okay, so I've got everything on Moodle, which looks like this. And I've already got a bunch of stuff up there. I record all my lectures and post them on my YouTube channel. So if you miss class or you want to hear me talk about something again, you can go on YouTube. Plus I've got every course recorded and on there back to 2018. So we've got the syllabus on there. I've got some links to some downloads. And I've also got a section here for resources for remote work. So this is a lab course, and the idea is for you to meet in the lab, at least during your lab times and most likely times outside of your lab times as well. If you want to get work done at home, you can remotely connect to the labs, or you can install a virtual machine. We have a virtual machine image available on Dropbox that you can download. And it'll give you, and I've also got a video on there that tells you how to set it up. And that'll work in Mac OS, Linux, or Windows. And so you can, we have the virtual machine image set up with the same software as you'll find in the labs. So that way you won't have to, working remotely is kind of cumbersome sometimes. Especially because the VPN will, if you have to go through the VPN, it slows down your connection. So all the instructions for that are on there. We'll have quizzes once every 1.5 weeks or so, which will be posted on there. The projects are posted. I already have Lab 1 posted on there. And then all the lecture slides and links to the lecture video and recordings will be on there as well. I've also got, I'll send emails out through Moodle, so make sure you check your email. And your grades and your project submissions will all be done through there. Okay, so that's that. We got a textbook, which is this one. Digital Design and Computer Architecture by Harris and Harris. This is a good reference. The only difference is I switched to the RISC-V processor instead of MIPS. This one still covers MIPS, like you learned in 212, but they're very similar. And I actually follow the conceptual part of this course, which is in the second half of the semester, follows this book pretty closely. So it is useful, but it's not, not, you can get by if you don't buy it, but it's a useful text. Okay, we got the course learning outcomes there. Those are just the ABET learning outcomes. I've listed important dates. We only meet for lecture once a week, so we have 14 lectures. So we'll be back here next week, but then we have Labor Day, September 5th off. And of course, lab was canceled on Friday. As I mentioned, we have 2 teaching assistants, Angela and Soyash. They're both based out of my lab in the Story building, the corner of Assembly and Blossom, room 2236. We don't have office hours for them set up yet, but we will, and we'll be announcing those soon. My office is also in the Story building. Feel free to stop by or call or email me. I'm pretty much here every day, all day. If you go to the next page, I've got the grading structure. This is a little bit unique because the grade you get in this course has about 55% of your grade is based on projects, and 45% is based on individual work, the midterms and the quizzes. But if you add up all of the weights, it adds up to 117%, 117.5%, which means that you can basically drop a project or an exam if you want to. So you can kind of customize this course based on whether you feel stronger with the conceptual materials and taking the exams, or if you're more into working in the lab and you do better in the more applied as opposed to the conceptual parts of the course. I used to say, you can drop an exam or drop a lab, but then the math started to get really complicated, so we just had the whole thing add up to 117%, and then the grading scale is the standard grading scale, which is A is 90 and above, and then we have B plus 85, B is 80, and so on. Section 9 shows the approximate schedule. Things toward the end of the semester get a little dicey because, projects tend to get compressed a little bit at the end, and then we don't have class, we miss a class or we miss labs for Thanksgiving, and then I am gone on November 14th for a conference, the supercomputing conference. I run a meeting there. And actually the lab, I actually say, if you look at November 14th, it says lab is none as well, but that's actually a typo. That was back when the TAs went to that same conference. My TAs now are not going to that conference, so we will have labs. So I'll send out an updated syllabus for that. If you have any disabilities that we can accommodate you for, then you need to register for those. I have the website there. There's a syllabus, tends to be slightly updated every semester for things like that. But more or less, we've been teaching this course pretty consistently for the past few years, so that there won't be any major changes. Yeah, the electronic resources, I already mentioned that. Grading scale, I mentioned that. Academic honesty policy is also a little different in this class. We're going to be using CAD tools in the lab. They are electronic design automation tools where you design hardware. You design digital logic hardware, and then you compile it to a programmable logic device called an FPGA. The CAD tools have been around. The CAD tools that do that have been around for a long time, about 30 years, but they still suck. Terrible to use. They kind of, you get the impression when you're using them that they're written by like a high school intern, even though they're real expensive and they're kind of high-end tools. I don't know why. Never figured that out. So when you're in the lab, you're welcome to ask other groups if you can get some pointers or help with the tools, like if the tools are crashing or giving you a confusing error message. But obviously you can't copy designs. Okay, we also have the attendance policy is, it's optional. As I mentioned, I post the recordings on YouTube. I found that most students want to be here and see the lectures in person, and they also want to be in the lab, and you get much more help if you're in the lab. So, but it's up to you. We have group work, and all the labs are group-based, group size of 2 members, so you'll need to find someone to work with for this semester. The grades you get on the labs will be the same for both members of the groups. Now, as you know, you guys are mostly seniors. You know that whenever you work in a group, it's nearly impossible to have both people contribute equally, right? So we don't really have a mechanism in here for dealing with someone who doesn't do anything, but 45% of the grade is individual, so it's not as if one group member could pull the other group member up for the total course grade, right? So as I mentioned, group sizes of 2 are preferred. Group sizes of 1 are allowed based on the availability of the workstations in the lab. I think we have 22, something like that, 22 machines in the lab. And so, as long as we have enough machines and, to accommodate single groups, that's fine with me, single person groups. Although you're still expected as a single person group to do the same work that's expected of the two person groups. Your project submissions, so you're basically designing a CPU. If it doesn't work, it's kind of hard to give partial credit. We try, and we've tried different mechanisms. We've done things like, sometimes some semesters we do demos. Some semesters we have you write a report and just grade the report. Some semesters we try to look at your code, but it's not practical to actually run everyone's code because you're not just running it. You have to deploy it to a board. You have to compile it and put it on an FPGA board. So you're building hardware. So at the very least, we do the best we can to accommodate partial credit. But at the very least, your projects have to compile. The hardware and the software have to compile. The late penalty, though, is very lax. There's a 7.5% late penalty for each school day after the due date, but it's capped at 30%. So even if you turn in all the labs, the last day of the semester, you're only going to lose 30%. The reason we do this is because the labs build on top of each other, so you can't skip one if you're falling behind. And every semester we have a few groups that kind of fall behind, and then they try to catch up at the end. So we limit the late penalty to just 30%. But you can only submit one version of each project. We learned that the hard way. And that's it. Okay, so that's the syllabus. Any questions? Yes?
If we submit another submission before the due date ends, will you just grade the latest one?
We're only going to grade one. Yeah, that's a good point. Yeah. So if you submit 2 before we grade, then we would grade the latest one. Yeah. Yeah. Yes.
Midterm date?
Sorry?
The date for the midterm exam?
Yes. I think I have it on there. Do I? Let's schedule.
The approximate. October 24th is the approximate.
Yeah, midterm October 24th.
Oh, okay, I see. Thank you. It's not in the 6th week.
We have a final exam is December 9th at 4. I base that on, now this is this course meets at non-standard time, so I base the final exam on whatever you get when you look up the final exam for a Monday, Wednesday class. So hopefully, for those of you in section 2, hopefully you don't end up with a conflict with the final exam. If you do, let me know. But actually, the final, I think in the last semester we just gave it on Moodle and we gave you the whole week to take it. So I expect we'll do that again. So I guess the point is moot. Yeah, and the project submission cutoff is December 2nd. So make sure you get all your projects in by December 2nd. Okay, let's go ahead and get started. Okay, so this class is a sequel to 212. Hopefully you all remember 212 really well, even though it's been 2 years since you've taken it. So in 212, you guys designed, hopefully, you should have designed some hardware in 212. If they taught it the way they should have taught it to you. So you design circuits using Boolean algebra or by hand drawing gate level design schematics, right? And then you deployed them on a breadboard, hopefully. So that's digital design. This course is advanced digital design because obviously this is a great tool to learn digital design, but it's not no one uses that in practice. A modern CPU would take 8 million breadboards to do it that way, and it would be impossible to debug because, as you know, it would be it's a giant nest of wires once the design gets complex enough. So in this course, we're using an actual industrial method to do digital logic design. We use these boards. In fact, we use the same boards now in, you might have used these already in 313. We use these in 313, 317, and 611. So we get a lot of mileage out of these things. These are FPGA boards. FPGA stands for Field Programmable Gate Array. And the idea is that an FPGA is a it's a programmable logic device that starts up as a blank slate. When you power it on, it's just a paperweight until you electronically configure it to behave as a hardware circuit that you've designed. So, when you power it on, it's nothing, and when you configure it, it sort of becomes hardware that sort of materializes. And then the design is stored in volatile memory. So if you power the board off, you lose the design, although typically these boards, and this one included, have a non-volatile memory that's off chip that automatically gets loaded in when you power it on. So when you power these things on, it comes up into a default configuration that's actually someone's design. It was loaded from the SRAM, or the flash RAM on there. So the way you program FPGAs as well, or the way you design hardware for FPGAs, as well as the way that you design digital hardware for an ASIC, like just a regular chip that you fabricate, is through this technique called hardware description language, HDL. It's a high-level programming language that's used to describe circuits. So it's basically the same thing you did in 212, but it's more readable, it's more reusable, it's more debuggable, and it allows you to design much larger scale systems with hundreds of millions of transistors or gates. Right? And so here's a little example of a little snippet of Verilog that implements this circuit. This is the HDL we use, is called Verilog or System Verilog. So you start out here with a blank slate when you power it on, and then you basically compile this System Verilog design and use that to electronically program the FPGA, and now you've just made hardware. You've just made a circuit. And so basically, we're extending the techniques you learned in 212 to design hardware, and then the other half of 212 was how to design a CPU design, microarchitecture. So you guys studied the MIPS. Actually, I'm sorry, 211 is where you design the circuits, and then 212 you design the CPU. And so in this class, we're going to also design the CPU, except we're actually going to build it on the FPGA. So while you're learning this System Verilog language and FPGAs, you are also going to be learning about microarchitecture and how to design and deploy a CPU. And we chose a CPU just because it kind of kills two birds with one stone. It reinforces the ideas of microarchitecture that you learned, and it also gives us an excuse to design a big logic circuit. A CPU is a big logic circuit, right? And so that's basically it. So we're learning HDL, and we're using it to build a CPU. So you might say, why study hardware design? Well, obviously, if you're a hardware engineer, the salaries are much higher than programmers and software people, because as you'll learn in this class, designing hardware is much more difficult than designing software, and more specialized. Cracks me up that Apple's average salary, $180,000 per year. Very competitive to get in there, though. Okay, so you might also wonder, well, why do we need to be designing CPUs? You might be aware of this idea about Turing completeness. It means that a CPU that's Turing complete can basically run any program that could be written, right? So what that means, the caveat there is that if you look at different types of computers, from the Summit supercomputer, which I think is still the fastest computer in the world, it's 200 petaflops, which is 200 quadrillion floating point operations per second, uses 10 megawatts. It has 2.4 million 64-bit processors in it, all the way down to essentially an Arduino. If you guys are familiar with Arduinos, they're little 8-bit processors, and they do about 200 kiloflops per second. The supercomputer is 10 megawatts, the Arduino is 20 milliwatts. But there's really no program, any program you can run on the supercomputer, you can run on an Arduino, right? They're all Turing complete, right? So the question is, well, why would we need to design new CPUs? What's the point? We've already got ones that do everything we need to do. And there's several different answers to that. One of them is that you'll notice that all of these systems right now are limited by their energy efficiency. So this machine is a 200 petaflop computer, and the goal is to develop an exaflop computer, which would be 5 times faster. Currently, it's impossible. The Department of Energy has been trying. They were supposed to have it done several years ago. Can't make it happen. It's not practical because it would. There's several practical reasons, but probably the most important one is the power requirements. They can't get enough power in there to power it. And so the goal with that is this one is about 20 gigaflops per watt. That needs to go higher, so we need more efficient hardware, more energy efficient hardware. But at the same time, even if you go down all the way down to the scale of embedded systems, the goal there is to make processors more energy efficient so your battery in your phone lasts longer, right? And you can do more with a mobile device. The other thing too, and you might have noticed this, but there used to be this thing called Moore's Law. I don't know if you guys have heard of that. So in the old days, specifically according to this, between 1986 and about 2003, CPU performance would double every 18 months to 2 years. So if you needed a faster or a more efficient computer, you could just wait 18 months and you'd get double the performance of your old one. So the problem there is that that's been slowing down. So you can see that in that interval, it was performance was going up by 52% per year. And you might say, well, how's that? Wait a minute, how's that translate to Moore's Law? Well, the yearly improvement rate, in order to double your performance every n years, would be e raised to the power of log 2 over n. So if you want to double every 18 months, you better be getting 58% improvement per year, which is about what we were getting there, 52. Every 2 years would be 41%, but you can see that, since 2003, it's been way behind that. And generally speaking, now, basically CPUs don't get in faster at all anymore. You get one generation to the next, they're exactly the same speed. If you don't believe me, I also, I like to collect these. That previous figure was from the computer architecture textbook. This table was actually mine. I collected this data myself, just going on Intel's website. And so I wanted to look at the last 10 years of CPUs. This is a little out of date now. I haven't updated it this year. But if you look from 2010 to 2019, that's the west mirror of the coffee lake. You can look at, I like to look at performance indicators, which indicate the peak performance of a CPU. Now, you don't always actually achieve your peak performance. In fact, usually you get 60% of your peak performance at best. But all of these factors that I've listed in this table, each one of these columns is an indicator of the peak potential performance you can get out under ideal conditions, right, in a perfect world. So it's kind of like the upper bound for the performance for each of these. So basically what I'm looking is the upper bound. This is not benchmark results or actual results, but just upper bound performance results. So you can track like the technology from 32 nanometers down to 14 nanometers. That's only a 17% improvement per year over 10 years. That would double every 4 years. Keep in mind that this is this technology node is only one side of a two-dimensional area on the chip. So the scaling factor is the square of that. Max clock rate's kind of doubling every 18 years at this point. Integer instructions per cycle per core, doubling every 10 years. Core is doubling every 5 years. DRAM bandwidth 7. The only one that's still kind of improving at a pretty good pace here is floating point throughput, the number of floating point ops per second or per cycle you can perform. However, no one uses that on a CPU. If you're doing floating point, you're going to use a GPU. So that's useless. And Linus Torvalds argues that there shouldn't even be floating point on a CPU. It's totally useless, according to him anyway. And then level 3 cache is every 6 years. over the 10 years. And I think this would actually look worse if I brought this to 2022. So CPUs aren't getting faster anymore. So, oh, and this is just a little anecdotal thing. I always, I like this. When I was a kid in the 80s and 90s, computers, it was crazy, because you guys might have never seen this, but computers always had a button on the front that was labeled turbo. And you would expect if you turn on turbo, it would go into turbo mode, right? It would go faster. But it turns out turbo mode, it's funny, the turbo mode made the computer run at its native speed, at its natural speed. And if you turn off turbo, it would cripple it. It would actually downclock it. And the reason for that was because machines were getting so much faster that it would actually break software. Like you would get a new computer and your old flight simulator would not be usable because it would be too fast. So that was the reason they put that on there. Obviously, you don't have turbo buttons anymore because computers don't get faster anymore. Okay, so you might be wondering about there's a lot of capabilities that are performance related that have been coming out, especially in the embedded space. So, for example, I mean everyone knows that video games are getting better and better, but if you look at things like actual new capabilities that we didn't have prior to their introduction, like there was no self-driving cars before 2014, there was no 4K video on a phone before 2015, no Face ID before 2017, no Animojis or real-time video tracking until 2017, and there was no computational photography until 2018. That's where you can take a picture and simulate having an expensive lens by blurring the background. None of that stuff existed, and all of those things they exist because the performance of the system permits it. They're all real-time applications, basically. And so you have to maintain a certain level of computational performance. So you might say, well, wait a minute. What you're saying is you're contradicting yourself. You're saying CPUs aren't getting any faster, but yet you're saying that there's all these new capabilities that are coming out that are enabled by performance. So what's the deal? Well, the answer to that is if you look at a die photograph, which die is the chip, and in this case, I've labeled the part of the chip that is the CPU. And you can see that only a small part of these chips are CPU. The rest of them are all specialized processors, like you can call them coprocessors or accelerators or domain-specific architectures. But basically, they're circuits designed for a specific application. In other words, someone said, we want to do something, we want Face ID, or we want Animojis, so we know the CPU just can't do it. The CPU is just not powerful enough to do it. So we'll design a circuit that just does that and put it on the chip. So a typical processor will have a very small part is the CPU, the actual, what you think of as a computer, the multi-core CPU with a cache that you can program in C or Python. But the rest of it is all processors that you write code in assembly language, and they can really only do one thing that they're designed to do. Like GPUs, neural processors, image processing units. There's all kind of crypto processors. There's all variety of coprocessors on these chips. And these are embedded. So typically, in this case, I think Apple is about 12% of the chip is CPU. The rest is specialized stuff. And even if you look at desktop processors, so one thing I like about Intel is they actually, see actually these pictures from Apple, these are bootlegged pictures. There's a website called iFixit, I think. There's a website where every time a new iPhone comes out, they tear it apart and they actually remove the die from the carrier, the package, so they can take a picture of it, and then they try to guess what's on it. A lot of these, like they say, this is the GPU up here. A lot of these are them guessing. These are not released by Apple. But Intel, on the other hand, takes a different approach. Every time they come out with a new processor, they actually label it for you, and then they ship out the die, the micrograph, the microscope image of the chip. And that's interesting because if you look at those over the past few years, this is Westmere, this is from 2010, you can see that 72% of that chip was CPU and cache. And then you go to 2013, that is the Ivy Bridge, and you can see that the processor part is shrinking. Now it's 47%, Now the die is changing too. That's a 160 square millimeter die. So the die is varying as well. It's a little hard. And that's a 4-core. The previous one I think was a 6-core. But you can see that there's a trend. The CPU and cache 47%. The rest of it's basically GPU and specialized I/O. This is the Broadwell chip from 2015. This is 20% of the chip is CPU. The rest of it's graphics processing. They say graphics, but it's video and graphics. Yeah. So, and then they have this display engine, system agent, display engine, memory controller. That's all special circuits, specialized circuits. So the point of this is that it used to be, back when I started here 20 years ago, there weren't a lot of hardware design jobs. There are very few, and those ones, I think most of those were not in the U.S. Because for the reasons I gave, you didn't need to design new hardware. Nowadays, you need to. Every new capability you get in your phone is from some hardware designer making it. So there's a lot more. It doesn't mean there's still infinitesimal compared to programmer jobs, but there's an increasing number of people working in the hardware space because that's really the only way to boost performance anymore. So here's just a couple other stats. The Qualcomm Snapdragon 830, this is a little out of date, but I was trying to figure out how many different co-processors some of these things have. So for example, the NVIDIA Xavier, which is the self-driving car one, has 8 GPU cores, a deep learning accelerator, a programmable vision accelerator, which is a VLIW processor, very long instruction word, and of course that's all in addition to the CPU cores. So the CPUs basically just run the operating system. That's really all they do. They don't do any heavy lifting. And then in the data center, of course, everyone uses GPUs and various other types of accelerators. And you might say, well, why are CPUs so slow? Well, basically, everything boils down to, in the world of computer architecture, everything boils down to now the memory wall and the power wall. The memory wall is when you have an application whose performance is limited by the memory bandwidth to off-chip memory. So really fast CPU, but you got a bottleneck to the memory, right? So the CPU's utilization is kept low because it's spending all its time waiting to get stuff from the memory. So a specialized processor can solve that problem partially by creating a specialized memory structure that's tailor-made for the application, right? So if you're doing machine learning, they bring in data as matrices, and they store it in a scratchpad memory that's controlled by software, right? And then there's the power wall, which is a limitation too, where you can't dissipate more than 2 watts per square millimeter of chip, or the system catches on fire. And so if you start to approach that during runtime, the chip has to self-throttle itself down. So you end up with limiting your utilization because of that. So even if you have this really cool chip, CPU, it's difficult to use it, to utilize it. So domain-specific architectures, they get around the power wall by basically making the architecture lean and mean. They eliminate all the overheads required by a general purpose processor. So they have, basically like the Google Tensor unit, which runs the machine learning workloads at Google. It only has like 7 instructions because that's all it needs. And so all the other decoding logic required for all the instructions, not needed. Okay, so in this course, I mentioned we're going to be using the FPGA boards to give you an idea of the process you have to follow to design large-scale logic circuits. I've got the course organized where the first 2/3 of it, so weeks 1 through 10, I'm going to try to teach you the tools as fast as I can, because otherwise we can't I want to be able to get you started in the lab, because as you know, this class is divided evenly between lecture time and lab time. So I got to get you up to speed in the lab as fast as I can. So most of the stuff I'll be presenting is applied, right? So you might think, you might get the impression, well, is he just teaching a skills course here? Is this a vocational school? What's going on? But no, I'm just trying to get this. There's some practical knowledge I have to get to as quick as I can. But in the last third, you'll have enough to basically carry through the CPU design to the end. And so the last third of the class is concepts, is more theoretical stuff. So I'll teach things that we don't use in the lab projects, stuff that you just basically have to know as like a traditional course. So that's the way I've got it set up for now. So one of the things I have learned over the years of teaching this class is that a lot of you don't come in knowing everything from 212, either because it's been too long since you've had 212, or because some of the instructors, we have a whole variety of instructors that teach 212. Some of them are better than others. Some of them don't focus as much on, say, assembly language, right? And the reason they don't is because some of the instructors in our department don't see the need for you to learn assembly language because no one programs in assembly language. And they're right, no one does. Use compilers. Compilers are really good these days, so you don't need to write any code in assembly language. That is it's from a bygone era. However, for this class, you have to know assembly language because, as you know, the assembly language is the native language of the CPU hardware. It's the language that the CPU directly executes in the hardware, in the circuits, right? So you can never be able to design a CPU if you don't know assembly language, because the goal of the CPU is to be able to execute assembly language. So you have to know assembly language first in order to design something that executes assembly language, right? So in other words, there's this software-hardware interface that sits between the software and the hardware. Everything above that is assembly language, which is generated by the compiler, so you don't have to write it. But the underlying microarchitecture is what it's actually pulling those instructions in and executing it. So you have to know it. And a lot of the instructors and grad students who teach 212 are not aware of that. So as a result, I've changed things up a little bit. Now I start this course out with an intro to assembly language, just so I can get everyone, try to get everyone back up to speed. I'm going to go pretty fast. But if any of you are lost, or if you're a grad student who hasn't taken our version of 212, then let me know. There's an instruction set architecture. It's a term you might remember from 212, or sometimes it's just called architecture. It's everything you need to know to program a CPU. Right, so it's the assembly language, it's the way that you encode assembly language and machine language, it's all the addressing modes, it's everything you need. Typically, it's something that is released by the vendors, the CPU vendors, right? They want to get this information out there because it's the only way that someone can use their product, right? So it's not hard to find the assembly language of any processor. In fact, Intel used to actually, if you asked for it, they would send you like a big 3-volume physical copy of it for free. All you had to do is go on their website. I don't know if they still do that or not. It's send you a big, like this thick, 3 big volumes. Everything you need to know, program it, the CPU. But the microarchitecture, which is the under the hood, it's how the assembly language is actually executed, or the machine language, I should say. That's a jealously guarded secret. That's a trade secret. So you won't find anything out about how an Intel processor works internally. They'll never release any information about that at all. So we don't even know basic things like, the cache works pretty well. Is it prefetching? Is it trying to predict what data I'm going to read in my program? Unclear. No one knows. Unless you work at Intel. There's just basic stuff like that. Like, how does a branch predictor work? Is it a tournament predictor? Unclear. Secret. I won't tell you that. But anything you need to know to program it, that's the architecture. The way that it works internally is the microarchitecture. You're probably aware of this. Instruction set architectures, there's quite a few of them. There's the Intel x86, i84, Alpha and Spark are no longer with us. Those were more specialized processors. Spark, they still make Sparks actually. They don't make Alphas anymore. And of course, ARM processor is the one that's in your cell phone and your tablet. It's an embedded processor. MIPS is the one you learn in 212. MIPS used to be used in gaming consoles and cable boxes, but not so much anymore. It's kind of disappeared. And now the new one that everyone's talking about is RISC-V. That's the big deal now. So the thing that's remarkable about RISC-V is that all of these other instruction sets, with the exception, I think, of Spark and MIPS, I think after RISC-V came out, they opened themselves up. But it used to be historically that even though, as I mentioned, CPU vendors put the instruction set architecture out for free, they give it to everyone. If you build a CPU that implements that, they'll sue you. All of them were like that, including MIPS. MIPS would come after you. They even went after textbook publishers. Like if you wrote a textbook for computer architecture and you took, like Hennessy and Patterson was constantly fighting with them legally. Because they don't want people to know how the CPU works. They don't want people building the CPU. They don't want people building the microarchitecture. They're fine with you writing code or writing a compiler. They don't want you building it. So this was a huge problem for decades. We barely could teach this stuff, how to build a CPU, because they were so aggressive. And then finally, they came out with this RISC-V, which is basically an open source. Anyone can use it. It's designed, anyone could build their own RISC-V processor. Actually, ARM is so Apple and NVIDIA have to they make their own ARM processor, but they have to license the instruction set from ARM. And then, before they can release the new processor, they have to send it to ARM so they can make sure that they did it right. Right? If they don't, they could put the kibosh on the new iPad processor. So now everyone wants to go to RISC-V. And so as a result, we've decided to switch this course to RISC-V because it's the new thing, right? We're hoping that in the future RISC-V will kind of take over and it'll knock ARM and Intel out of here. I don't know if that'll ever happen. Now you might say, well, geez, we learned MIPS, now we're going to learn RISC-V. How many? They're very similar. In fact, RISC-V is actually designed to make it easier to build the underlying CPU. So if you looked at the number of lines of code students in this class used to have to write to get MIPS working, it was actually much less than now with RISC-V. RISC-V simplifies some of the kind of the more boneheaded decisions they made in MIPS that made it more difficult. You might remember, like, for example, I don't know if you remember from 212, but in MIPS, there were R-type instructions, which were register instructions, and then there was I-type instructions, which were immediate instructions, right? So, for whatever reason, the destination register field was different in both. Why? There was no reason for that. That required you to add extra hardware to deal with that. It was dumb. RISC-V fixes that. So it eliminates some of the miscellaneous muxes and control logic that you had to put in to fix the dumb decisions they made in MIPS. Right. So, but I'm going to go through, I'm going to cover RISC. Okay, so I already talked about that. I think I already covered this too. The instructions are, as you know, as you hopefully remember from 212, instructions are the native language of the processor, right? It's from the perspective of software, each instruction is atomic. It's like the smallest unit of work from the perspective of software, right, that a CPU can do. And so, for example, one line of C++ code might require 1 to 10 instructions. One line of Java code, Java's more abstract language, so it's going to be like 10 to 100 instructions. And one line of Python code might be 1,000 instructions, right? Because Python is a very abstract language. You can do a lot of stuff in one line of Python code, especially when you use, dictionaries and the crazy, memory data structures that you can use. And then instructions themselves are identified by their mnemonic, which is basically like a 2 to 5 letter shortened abbreviated name. And then after the mnemonic, you've got some addresses, register addresses, memory address, operands, right? And so that's how assembly language looks. I mentioned that RISC-V is similar than MIPS, RISC stands for Reduced Instruction Set Computer. This is just some background for where this stuff came from. reduced instruction set computer is this concept where if you look at the execution time to run a program, it's the number of instructions that are executed to run the program multiplied by the amount of time required per instruction, right? So a CISC architecture, which is like the Intel processors, and things like digital signal processors, which have very complex instructions. The idea is that you want to minimize the number of instructions to run the program because each instruction does a lot of stuff, right? But the problem is that it increases the time per instruction, right? Whereas RISC, you minimize the amount of work done per instruction, but it increases the number of instructions per program, but it speeds up the individual instructions. So it's kind of a trade-off, right? You can maximize one, minimize the other. The problem, though, with RISC is, and I'm sure you guys know this, is that because the instructions are so simple and they do so little, each individual instruction does so little, that you got to write a ton of instructions. So when you write your programs, there's all these instructions. Every little tiny step has to be an instruction. So that makes it difficult to write an assembly code, but you're not supposed to be writing an assembly code. Compiler's supposed to be doing that for you. So when you sit there, now you're going to have to write some programs in this class to just buff up on your RISC or your assembly language, and also you're going to have to write some programs that will test your CPU. You have to write test programs, test benches, right? And you'll think to yourself when you're writing those, man, this is painful. This is just awful. But RISC is designed to be awful. That's the whole point, is that the programs the instructions are very simple, and so comprising a program that does something meaningful to get an abstract behavior requires a lot of sort of tedious steps. But we try to minimize the amount of assembly language programming in this class because it is pretty awful. But you got to know enough in order to design the underlying circuits, right? That's as I mentioned. Okay, so RISC is very much like MIPS. In fact, you probably can read it right now just from what you learned in 212. It has 32 registers. The registers in RISC have names like the ones in MIPS. They have little code names, so you can just refer to the registers by number from 0 to 31, or there's little code names S0 to S11 are supposed to be preserved across function calls. T0 through T6 are temporaries. A0 through A7 are arguments. And then there's the return address, the stack pointer, the global pointer, and the temporary pointer, which none of those you really have to worry about for this class except for the return address. And then there's this one register that's always 0, which is called 0, and it's also number 0. Okay, so just a quick refresher here. So here's an example instruction where you can add 2 registers, B and C, and write the result in A. A, B, and C represent registers here. So B and C are the operands. Those are the inputs. They come last, and the destination comes first. So just like in MIPS. So if you have a line of code like this in C, or Java, or Python, where you have F equals G plus H minus I plus I, that line of code contains 3 operations, so you need 3 instructions just for the arithmetic there. But the problem is, and this is the reason why assembly language is awful, is not so much because this gets translated into 3 separate operations, because each assembly instruction can only do 1 operation, and this line of code has 3. It's not just that. It's the other problem is you have to load those variables into registers and then store the result. And you have to keep track of what is in every register. That's why it's hard to write in assembly language. And then you can also have immediate operands where you just put a number there. So let me skip ahead a bit here. So I put together what I think are the top, currently, my running list of the 6 biggest challenges writing assembly code. Right? And I'm hoping that by explaining these to you, I can also sort of teach you the language as well, or refresh your memory. So the first challenge, in my opinion, is, as I mentioned, having to load and store separately from the compute. So you have to get the data from memory because it's a load-store architecture. So you always have to get data from memory because there's this idea that there's a memory hierarchy. There's registers and there's memory, right? So you got to get the data from memory with load instructions, and then you number crunch it. and then you take the result and you store it back to memory. So it's always load, compute, store. Load, compute. That's always the pattern that you see in the code. So it used to be with CISC architectures, the old Intel architecture, you could just embed variables directly into instructions, right? So you could just say, hey, add G and H, and put the result in foo, add I and J and put the result in bar, and foo and bar are just temporaries because they represent the sub-expression values, right? The two sub-expressions that I have in parentheses. And then you could just subtract foo and bar, store to F, right? But the problem is you can't because the instructions can only do a memory operation or an arithmetic operation. They can't do both at the same time. So you have to, load 4 times, 4 variables, and then store the result, right? The problem, though, is you have to remember which registers you're using. Another thing that I hate is the fact that when you do decision code, conditional code, the problem here is that if you say A is less than B, right, do something, and then you have an else block, right? Everyone is familiar with that structure. Every high-level language has a structure like that. If, then else, right? The problem is in assembly language, it doesn't work that way because when you have an instruction here called branch if greater than equal, branch if less than, right? The problem is that generally speaking, you expect the if part to be at the top and the else to be at the bottom, right? But in assembly code, the only way to do that is to actually complement the logic of the if. Because the idea is that if the if part is below the condition, then you want to tell the assembler to skip that if you want to go to the else part, right? Which means that the test has to be the opposite of this. So you can't say if A is less than B. You got to say if A is not less than B, then skip the next block of code. That's the then part, right? And go to the else part, right? So notice I say branch if greater than or equal because greater than or equal is the opposite of less than, right? So if it's greater than or equal, skip. I call it else actually. I go to a label called else. And then after the then part, I have to have an unconditional branch to exit so I can skip the else part. So if I'm in the then part, I got to skip the else part, right? So this is kind of the opposite of that. So semantically, you have to make that translation, right? I don't like that. But that's one of the things about assembly language that makes it difficult. Sorry, I forgot I highlighted that stuff. Another thing that RISC-V and MIPS lack is an index. You can't use an index to an array. I don't know if you guys remember that. If you ever write a program that walks through an array, because it sorts it or adds up numbers or whatever. Anytime you traverse an array of any kind, arrays are very common in programming languages and code. So you're doing a lot of array access, right? Vectors, matrices, images, coefficients in machine learning, they're all arrays. But when you walk through an array, you can't say like vowels of x1. You can't say, I'm going to give vowels as my address, I'm just giving an index register. No, can't. So you got to do this really kind of annoying thing where you have to load the address of your starting point of the array into a register. And then as you go, you have to add the size of each element, which is 4 because it's an integer array. It's 4 bytes each. You have to add to the starting address as opposed to having just an index, like to put a bracket index, right? You can't use an index. You have to basically do this address calculation, right? Now, the problem with that, you might say, what's the big deal? Well, the problem is you also have I. So I increases by 1. But yet the index into the array has to increase by 4. So notice I have to add 4 to my address. I have to add 1 to my I. That's terrible. Because I have to compare I to 100. Which assumes that I'm incrementing it by 1, right? So that kind of stinks, right? I don't like that. There should be an index register. Yes?
Might be a stupid question, but is it always possible to just, in your head, multiply 100 by 4?
Yeah, some people do that, but you could do that. That's actually kind of easy to do if it's a constant. If it's not a constant, if it's a variable, then you have to multiply the variable by 4. You could do it that way, sure. Yeah, that's kind of an optimization that you could do. But again, even if you do that though, that's still not a direct translation of the high-level code, right? So it's not straightforward. So the other, this is also related to keeping track of array addresses and loop counters separately. That kind of overlaps a little bit the last one, where in this case I'm copying one array to another part of memory. I'm copying source to destination. I had to have a separate pointer register for dest and a separate pointer register for source, and then I had to keep track of those separately, and then of course the loop counter. And then finally, I think the last one here is allocating registers. So you have to keep track in your mind or in comments. It's always helpful to have comments. But you have to keep track of what value is in each register, and you have to be able to know when you can recycle the registers. Like when one register is done, or one value is done, you may want to reuse that register. Registers are a scarce resource, so you have to recycle them, right? You got 32 registers, so those registers will hold different things at different points of the execution of your program, but you have to keep track of that. Sometimes you forget, use the wrong register, and now you've got a bug. So those are the, oh, and there's one last thing here too. There's no branch, there's no instruction where you can compare a value to a constant. So you can't say like, branch if register x1 is less than 0. You can't do that. The reason is because the branch destination, which is exit, is stored in the immediate field, which means there's no space left over to put that 0 anywhere, right? So as a result, you have to preload the register. Every time you compare a value to a constant, you have to load a register with that constant and then compare the registers. Now you might say, well, come on, you're splitting hairs. You do that a lot. That's a very common thing to do in a program, and you're constantly having to add instructions to deal with that. Yes?
In this specific case, could you use the 0 register?
Yeah, in this case you could, yeah, but if it wasn't a 0, yeah, that's a good point. In this case, but if it was anything other than 0, and this happens a lot like that with that previous case with the 100,
Yeah.
with the loop 100 times.
Mm-hmm.
Yeah, so anyway, those are the six things that I think are make it difficult to write in assembly language. But if you understand those, it's and you get used to it, you can get pretty good at it. Okay, so let's see where are we at here. Okay, so I'm going to skip around a little bit. So just to give you a little preview, in this course, as I mentioned, we're designing a CPU, and so the idea is that we want you to be able to say, when you're interviewing, that I designed a CPU from scratch and ran code on it. There's not many people can say that. I know that from experience from a former student who went to Amazon and was talking to the Berkeley and Stanford graduates that were there with them, and they said that no, they never did anything like that. So the final project in this class, because we've added a lot more, we've scaled back the projects a little bit, but right now the final project is to design your CPU and then write a short assembly code program that will make this board behave like a calculator, where you can select an input value using these switches, and then the processor and your program together, the hardware and the software, will calculate the square root of the value that you put in, and it will display that on the hex displays, on the little 7-segment displays. So the value you put in will be an integer, but when you calculate the square root, it's going to be a fractional number more than likely, right? And so the hex displays will display the fractional number where the first 3 digits are whole numbers, and then the other 5 digits are fractional digits in base 10. Right, so you got to worry about getting the switches in. You got to do the square root, and then you have to convert the result, which will be a fractional value. We're going to use fixed point arithmetic for that. You have to convert that to base 10, so you can display it in base 10, so it's human readable. right? So that should be where we end the semester on. That's our goal. So how do we get there? We got to design a CPU that will do a minimal set of RISC-V instructions. We've picked out 30, I guess, yeah, 30 instructions. The RISC-V instruction set has more than 30 instructions, but these are enough to get the job done. And it's actually pretty easy to add, usually pretty easy to add more instructions if you want. These are the same instructions that we used to have students put into their MIPS processor. And whenever a student would come in here and say, I don't want to write assembly code. I want to just use a cross compiler. So compile C to MIPS, and then I'll just write my code in C, compile it to MIPS, and run that on my CPU. And every time that someone does that, I say, well, you can do that, but there's no guarantee that the compiler won't generate an instruction that we don't have. But that never happened, believe it or not. GCC actually pretty much is restricted to these instructions. If you compile a simple C program, you're going to get a program comprised of these 30 instructions, more than likely. So we never had an issue with that. So you could actually cross-compile if you want to, but I can tell you from experience, it's such a hassle to set up. It's easier just to write an assembly code. And so the first set of instructions are going to be all arithmetic. And the second group of instructions are branch and jump instructions. We're not going to do load and stores because we're not even going to have a data memory. We're going to design the CPU without a memory. We're going to have an instruction memory but no data memory. Just for, to simplify things a bit. And actually that's wrong. That's it should be lab 2 and 3, I believe. I think the lab numbers are off on that. But that's the same, basically the two generations of the CPUs. Okay, so so how different is RISC-V from MIPS? I think these instructions are all the same. So we have add, subtract, and or XOR. Those are just arithmetic and logical. Then you got your shift instructions. Now one thing, shifts are different. You might have noticed in MIPS, when you had a shift instruction, the shift amount was a constant. Now it's a variable. You get the shift amount from a register. MIPS actually had a variant of the shift instruction called like shift left logical variable, where you could get the shift amount from a register. But that was kind of the secondary way to do shifts. But in RISC-V, the primary way to do shifts is with a variable shift amount. I don't even think you can do a constant shift in RISC-V, which is cool because you can?
I think so.
Okay, maybe. I don't think I've ever seen, maybe shift immediate. Oh, there is an immediate, yeah. Might be a pseudo instruction though. Or maybe, maybe it just uses the immediate field. I don't have to look at that. But yeah, there's, but these are variable shifts, so that's one difference from MIPS. These comparison instructions are the same, I believe. Multiplies are different. So you might have remembered from MIPS, when you multiplied, the results were stored in high and low, two special registers, which you then had to follow up with move from high, move from low. RISC-V has a multiply and a multiply high. The multiply high gives you the upper 32 bits of the result, of the product, I should say. Right? Now this is important for you guys because when you write your square root code, you're going to have to use this because when you do a multiply of two n-bit numbers, it is often the case that you need 2 n-bit product, right? You need twice the number of bits in the product from a multiply. And so the multiply high is a way to recover those upper bits. And like I said, we are going to need those in our program. And then there's a multiply high, multiply unsigned, because whenever you grab the high bits of the product, it's important to know whether it was a signed or an unsigned multiply, because you get different results. The actual hardware has to behave differently. Okay, bitwise, these are the same arithmetic, bitwise, logical, immediate, shift, oh yeah, there it is. I forgot. That's the shift immediate instruction there. And then we have branch and jumps, and I think those are those are pretty much the same. I think in MIPS, though, a lot of these were pseudo instructions, but these are all real instructions in RISC-V. They're all hardware instructions. They're not pseudo instructions. And then, of course, we have the load and store, and we're not actually using those in the core CPU, but we may use them in examples in the lab. And then load up or immediate. Okay. Any questions about that? Everyone with me so far?
Is that in the book, the Maria?
No, actually, the book uses MIPS. They haven't I don't think they've updated this book yet to RISC-V. Everyone else is moving that way in the academic text. They do have an ARM version of this book, so they have MIPS and ARM. They just, as far as I know, they don't have RISC-V yet. But the RISC-V instruction set is available online at riscv.org, and plus it's we give you all the information on Dropbox. In fact, if you go to the Dropbox here, I have a RISC-V reference card, which is a PDF, a little quick reference card, and we have a we put the RISC-V instructions and their encoding in the lab sheet now. So when we assign the lab, they're in there. We don't have a separate document on Dropbox for that. In lab this week, so first of all, number one, please start thinking about who you want to partner with. Right? Remember, they're 2-person groups, and we want you to just work with the same partner all semester. So find a partner, and once you do, email me. One of the partners should email me the names of the group so we can put them in our grade sheet. Because when you submit your projects, only one person has to submit. And then we'll see you on lab on Wednesday, or half of you. And we're going to just be going through some tutorials for RISC-V programming. All right? See you then.